For millennia, humanity has pondered the end of life, the end of Earth, perhaps even the end of the Sun. But what if the very fabric of existence, the vast expanse of the cosmos itself, were destined for an ultimate, cataclysmic conclusion? Not a slow fade into darkness, nor a fiery collapse, but a violent, tearing apart, a cosmic shredding that unravels everything we know, down to the fundamental particles. This is the chilling premise of the Great Rip, a theoretical fate for our universe that pushes the boundaries of our understanding of reality. Our cosmic story began approximately 13.8 billion years ago with the Big Bang, an event that birthed not only matter and energy but also space and time themselves. Since then, the universe has been in a state of continuous expansion, growing larger, colder, and less dense. This expansion was initially thought to be decelerating, gradually slowing down due to the mutual gravitational pull of all matter within it. It was a comfortable model, suggesting a universe slowly evolving, perhaps towards a stable, albeit cold, future. However, groundbreaking observations in the late 1990s threw this conventional wisdom into disarray. Astronomers, studying distant supernovae as standard candles to measure cosmic distances, made a startling discovery: the universe's expansion isn't slowing down, it's accelerating. This revelation sent shockwaves through the scientific community, implying the existence of an unknown force, a mysterious cosmic push, actively driving galaxies further apart at an ever-increasing rate. It completely redefined our understanding of the universe's ultimate destiny. To account for this observed acceleration, scientists posited the existence of dark energy. Unlike gravity, which pulls things together, dark energy appears to be a repulsive force, inherent to space itself, pushing everything apart. It's thought to comprise roughly 68% of the universe's total energy density, yet its true nature remains one of the greatest mysteries in modern cosmology. We cannot directly observe it, only infer its presence through its gravitational effects on the large-scale structure of the cosmos. Its properties dictate our universe's eventual fate. Before the discovery of accelerating expansion, cosmologists primarily considered two main scenarios for the universe's end. The Big Crunch, where gravity eventually wins, pulling everything back into a singularity. And the Big Freeze, or heat death, where the universe continues to expand, diluting all energy and matter until it becomes a cold, dark, empty void. The revelation of dark energy introduced a third, far more violent possibility: the Great Rip. This scenario suggests a dark energy that doesn't just push, but intensifies its tearing power over time. The Great Rip hypothesis is predicated on a specific, yet plausible, characteristic of dark energy, often referred to as phantom energy. In this extreme model, the density of dark energy doesn't remain constant, instead, it slowly but inexorably increases over cosmic time. This escalating density translates directly into an accelerating expansion that grows exponentially more powerful. As this force intensifies, it begins to overcome gravity at progressively smaller and smaller scales, initiating a chain reaction of cosmic dismantling, tearing apart structures from the largest to the most minuscule. The first victims of the intensifying dark energy would be the largest gravitationally bound structures, galaxy clusters. These immense groupings of hundreds to thousands of galaxies, like our own Virgo supercluster, are held together by the collective gravitational pull of their constituent members in vast reservoirs of dark matter. But in the Great Rip scenario, the repulsive force of dark energy would eventually become stronger than this combined gravitational glue, stretching and pulling these clusters apart, scattering their galaxies into isolated, rapidly receding islands in an ever-expanding void. Next in line would be individual galaxies themselves. Our Milky Way, for instance, is a massive spiral galaxy containing billions of stars, gas, dust, and dark matter, all held together in a delicate gravitational balance. But as dark energy's grip tightens, its outward pressure would overcome the internal gravitational forces binding our galaxy. Stars would be stripped from their orbits, the spiral arms would stretch and dissipate, and the entire galactic structure would be torn apart, its components flung out into the rapidly expanding emptiness, destined to drift forever alone. The destructive march of dark energy continues to even smaller scales. Once galaxies are unbound, the next target would be gravitationally bound stellar systems, stars and their orbiting planets. Our Sun and its planets, including Earth, are held together by the Sun's powerful gravitational pull. But in this scenario, the relentless expansion would eventually exceed the Sun's gravity. Planets would be wrenched from their orbits, becoming rogue bodies hurtling through an expanding, desolate universe, no longer tethered to any star, experiencing an eternal night. The terrifying progression doesn't stop there. As dark energy's density continues to swell, its expansive force would become so immense that it would overwhelm the internal forces holding planets and other celestial bodies together. Earth, along with every other planet, asteroid, and moon, would literally be ripped apart. The geological structures, the very material comprising these worlds, would be unable to withstand the accelerating expansion, reducing entire celestial bodies into their constituent rocks, then dust, then ever smaller fragments, dispersed into the void. This is where the Great Rip truly becomes cataclysmic. In its final, most extreme stages, the phantom energy would become so potent that it would overcome the electromagnetic forces binding atoms, and even the strong and weak nuclear forces holding atomic nuclei together. Protons, neutrons, and electrons, the fundamental building blocks of all ordinary matter, would be torn apart. Matter, as we understand it, would cease to exist. There would be no chemical bonds, no structures, just a rapidly expanding soup of fundamental particles, instantly separated and isolated. Imagine a force so overwhelming that it annihilates the very bonds that define existence. Gravity, which holds planets and stars, electromagnetism, which forms atoms and molecules, the strong nuclear force, which binds protons and neutrons into nuclei, and the weak nuclear force, which governs radioactive decay. Each of these fundamental interactions, the pillars of our physical reality, would be systematically overpowered and undone by the relentless, accelerating expansion. Nothing, it seems, would be immune to the ultimate cosmic shredder, leading to a void devoid of any structure. And then, the moment itself. The Great Rip culminates when the phantom energy becomes so strong that it literally tears apart spacetime itself. This isn't just matter being ripped, it's the very fabric of the universe, the four-dimensional canvas on which all events unfold, being shredded. In the final, infinitesimal fraction of a second, the expansion rate would become infinite, leading to a singularity where all points in space are infinitely distant from each other. No cause and effect, no light, no time, just an infinite void, infinitely expanding. What remains after the Great Rip? Nothing recognizable. No stars, no planets, no atoms, no light, no structures whatsoever. Just a universe composed of isolated, elementary particles, endlessly expanding away from each other at speeds greater than light, effectively cut off from any interaction. The very concept of here or there would lose all meaning. It would be a state of ultimate isolation and entropy, where the universe has literally consumed itself in an act of self-destructive expansion, leaving behind an infinite, cold, empty, and utterly featureless expanse. While terrifying in its implications, it's crucial to remember that the Great Rip, if it were to occur, is an extremely distant cosmic fate. Current estimations, based on our best understanding of dark energy, place this event billions, even tens or hundreds of billions of years, into the future. For context, our Sun is expected to run out of fuel in about 5 billion years, long before the forces of a Great Rip would even begin to dismantle our galaxy. So, while a fascinating and chilling thought experiment, it's not an immediate concern for humanity. It's important to underscore that the Great Rip remains a theoretical hypothesis, one of several competing models for the universe's ultimate fate. Our understanding of dark energy is still in its infancy. We don't yet know if its density is truly constant, if it will increase, or even if it might change its properties in other ways. The existence of phantom energy, which would drive the rip, is not yet confirmed. Scientists continue to gather more data, refine cosmological models, and push the limits of observation to unravel this profound cosmic mystery. Dedicated efforts are underway to better characterize dark energy. Missions like the Euclid Space Telescope are mapping the large-scale structure of the universe with unprecedented precision, observing billions of galaxies to trace the history of cosmic expansion. By carefully measuring how cosmic structures have evolved over billions of years, astronomers hope to discern the exact nature of dark energy, whether it's a cosmological constant, like Einstein's original idea, or something more dynamic and potentially destructive, like the phantom energy required for a Great Rip. The implications of scenarios like the Great Rip extend far beyond cosmology. They challenge our fundamental understanding of physics itself. If dark energy truly can overcome all fundamental forces, it suggests a profound incompleteness in our current standard model of particle physics and gravity. It forces theorists to explore new realms of quantum gravity, exotic fields, and multiverse theories, all in an attempt to reconcile the observed universe with a potential future that defies conventional wisdom. This pursuit of cosmic destiny is, at its heart, a quest for a unified theory of everything. Whether the universe ends in a big crunch, a slow big freeze, or the dramatic violence of a Great Rip, the ongoing scientific exploration of these possibilities highlights humanity's insatiable curiosity. To gaze into the cosmic abyss and contemplate the ultimate fate of all things is to ponder our own fleeting existence within a grander, incomprehensible narrative. The Great Rip, though a dark and distant specter, serves as a powerful reminder of the universe's immense scale and its capacity for wonder, even in its most terrifying and destructive manifestations.